Typically, I think people think of solutions as being a solid dissolved in water, and that's often what they are, especially in chemistry. But you can have a solution between any combination of phases. You can have a solution of two gases. An example of that is the air that we're breathing. Air is mostly nitrogen, but it also has oxygen and carbon dioxide and argon. You can have a gas dissolved in a liquid, club soda. You can have a liquid dissolved in a liquid, something like vodka, which is a solution of ethanol, a liquid, and water. You can have a solid dissolved in a liquid. That's what we're most familiar with. You can also have a solid solution where you have two solids that are dissolved in each other. This is called an alloy, a metal alloy. So brass or pewter. These are solid solutions. And obviously, you can't take iron and lead and just put them together, right, and have them form a solution. But if you melt them and mix them together, they will form a solution. And when they solidify, they will still be mixed homogeneously. So solutions can have all kinds of different phases. You can even have gases dissolved in solids. Kind of crazy. So any particular solvent will not dissolve every possible solute, which is good, right? Because if everything dissolved in water, we'd have a problem, right? When it rained, the trees would dissolve, the roads would dissolve. Things just would not last very long, right? So particular solvent won't dissolve everything. So we talk about solubility. And solubility can be quantified, or we can talk about it qualitatively. But solubility is how much of the solute will dissolve in a particular amount of the solvent. That solubility will depend on nature's tendency towards mixing, but it also depends on the types of intermolecular forces holding the solvent and the solute together. So we know that many physical systems tend towards lower potential energy. This is why a ball rolls down a hill and not up, because as it goes down, its potential energy is decreasing, and that is a spontaneous thing. If we think about the formation of a solution, this is not necessarily lowering or changing the potential energy in any way. Here we're looking at a tank with a separation in the middle. We've got argon gas on one side and neon gas on the other side. And if we remove that barrier, those gases are going to mix. Does that lower their potential energy? No, it doesn't. So there's got to be something going on besides just lower energy. So far, in Chem 1A, lower energy has been the answer to most questions of why does that happen. So there's another concept here called entropy. Entropy can be defined in several different ways. It's a little hard to put your finger on. We can say that it's a measure of the energy randomization or the energy dispersal within a system. We also sometimes talk about entropy as being related to the amount of disorder in a system. So what happens when those two gases are mixing, each gas has kinetic energy. Let's go back and look at this. Each of these gases has kinetic energy, but here the kinetic energy of neon is confined to this part of the container, and the kinetic energy of argon is confined over here. When the barrier is removed and they mix together, now each of them has spread out their kinetic energy over a larger volume. And that means that the entropy has increased. It has become more spread out. So energy tends to spread out or become dispersed. If you think about, the flame of a Bunsen burner or a wood stove at home or something, we've got this chemical reaction that's generating heat. Does the heat just stay right there by the flame? No, it radiates out. It spreads, right? back when the heater wasn't working in here, before they got the space heaters, we had, some Fisher burners set up here, blasting away like a campfire. It was all cozy, right? So there's a lot of heat right here, but after a while, the whole room got warmer, right? Because the energy spreads out. That's an increase of entropy. This explains why thermal energy gets transferred from hot objects to cold ones. You put ice in some hot coffee, and what happens? The coffee gets colder and the ice gets warmer. The heat spreads from the hot coffee into the cold ice. So energy is always spreading. So we mentioned intermolecular forces. These have a big effect on whether something will form a solution or not. And so, quick review of intermolecular forces. The weakest are the dispersion forces. Everything has dispersion forces. The next stronger are dipole-dipole forces, and these are between two polar molecules. Each polar molecule has one end that's slightly positive and one that's slightly negative, and so we can get attraction between those. And then we had that special kind of dipole-dipole forces called hydrogen bonds, where, remember, phone home? So if we have hydrogen bonded to nitrogen, oxygen, or fluorine, then that molecule can undergo or experience hydrogen bonding, and that's the attraction between two different molecules. It just forms an extra strong dipole. And then we've got the ion dipole force, which technically is not an intermolecular force, but this is very important in the formation of solutions. So this is the interaction between an ion, like sodium, and something that has a dipole, like water. So we have intermolecular forces that are holding the solvent together. Here we could pretend that the blue thing is maybe water molecules. And then we have a solute, and something's holding that together, right? If we're talking about salt a lot. So salt, why is it a solid? Because there are forces holding it together, right? Otherwise, if there weren't any force, it would fly apart and it would be a gas. Why is water holding together as a liquid? Because it has hydrogen bonding. The hydrogen bonding holds those particles together. We also can have interactions between the solvent and the solute. And so whether a solution forms or not is going to depend on the relative strengths and the types of those different interactions. So this is a phrase that chemists use a lot. Like dissolves like. And this suggests that if we have two substances that have similar types of intermolecular forces, they are much more likely to make a solution than if we have two substances that have very different types of intermolecular forces. So water is polar, has hydrogen bonding. Ionic compounds often dissolve in water because there's that attraction between the dipoles in the water, the ion dipole force, really. Miscible, we've seen that word before, and I said it's a lot like mixable, right? Miscible, that describes two liquids that are soluble in each other in all proportions. And an example of that is ethanol and water. If you have a glass of water and you put a couple drops of ethanol, that'll dissolve just fine. If you have a glass of ethanol and put a couple drops of water in there, that'll dissolve just fine as well. When you're thinking about solids and liquids, that doesn't work because you can't take your cup of salt and put a couple drops of water in there and have it make a solution, right? You've got some wet salt, and it's not really a solution. But with the water, you can put a little bit of salt in it, and it'll dissolve, form a solution. You can put more salt in it, it'll dissolve and form a solution. But at some point, there's going to be, you're going to reach a limit. But with liquids, we can have miscibility where they can mix in any proportion. So when we have a solution trying to form, we have to break the forces holding the solute together and break the forces holding the solvent particles together, and then we make some new attractions between the solute and the solvent particles. Well, if the solute-solvent interactions are very weak, and we had to break strong interactions, we have this entropy thing which is driving the mixing, but that might not make up for the loss of the energy in breaking those stronger interactions. And so this is summarizing that if we have solute-solvent interactions that are strong compared to the interactions that those two things had by themselves, we'll get a solution that forms. If they are even just equal, it will form. But if our solute-solvent interactions are weaker than those between the individual substances, then it's going to depend on the relative difference. We might still form if it's just a little bit weaker, but if it's a lot weaker, it won't. So I think I talked to you about, or gave you the analogy of Japanese and Swedish people in a room, right? Remember that one about the intermolecular forces and speaking the same language kind of a deal, right? So we can think of that here as well. So let's say the Japanese people are the solvent and the Swedish people are the solute, right? The Swedish people are speaking Swedish to each other. The Japanese people are speaking Japanese to each other. But when they try to talk to each other, they can't understand each other. So is this group of people likely to mix thoroughly? No, you're going to have clumps of Swedish people and clumps of Japanese people speaking to each other in their own languages, right? And that's what happens when you try to make a solution of two very different things. Like oil has dispersion forces. It's a nonpolar molecule. Water has hydrogen bonding. It's very polar. And so those are like two substances that speak different languages. They're not going to mix together, okay? So we need to have, that's where the like dissolve like comes in. Yeah, those interactions really are just the intermolecular forces. Yep. So you should be able to answer questions like this. Determine whether each compound is soluble in hexane. Okay, we didn't spend much time on it, but we did learn about a little bit about organic nomenclature. So hexane. You should remember that hexane is a hydrocarbon. It's got, yeah, that doesn't work. It's got carbons and hydrogens. And this prefix hex tells me how many carbons. It's 6 carbons, and then it's a bunch of hydrogens. The ane tells me this is all single bonds. So hexane, pentane, propane, anything like that, carbons and hydrogens. Is a carbon-hydrogen bond polar or nonpolar? Nonpolar. That's the one that I want you to remember. Otherwise, if I said any other two nonmetals, I would expect you to say, well, they're different, it's probably polar. The one you need to remember is carbon and hydrogen, nonpolar. This thing only has nonpolar bonds. So is hexane polar or nonpolar? It's nonpolar. So we should recognize that this is nonpolar. And then in order for these compounds to dissolve in hexane, they should also be nonpolar. Right? They should be like the hexane. Like dissolves like. Is water nonpolar? or is it polar? It's very polar, and it does hydrogen bonding. So water's not going to dissolve in hexane. How about ammonia? That might be a little harder, right? I heard polar, and polar is correct. But let's think about, well, how could we figure that out? Ammonia's NH3. You have to forgive me, my Apple Pencil has been dropped one too many times, and now it only works if I hold it vertically. So I'm having a little trouble today. So that's the Lewis structure for ammonia. And the guidelines I gave you were, this will be nonpolar if no lone pairs and everything bonded here is the same. Well, this has a lone pair. That means it's lopsided. That's a polar molecule. Does that dissolve in something that's nonpolar? No, because they don't know how to talk to each other. How about propane? That's nonpolar, right? Carbons and hydrogens, just like this one. Will that one dissolve? Yeah, almost certainly. How about hydrogen chloride, HCl? That's going to be polar, right? Here, I just have one bond. If the bond is polar, the molecule's polar. Those are different elements, so I would expect you to say that that's a polar substance, not going to dissolve in hexane. So answering questions about what's soluble, you're looking for common polarity, right? Is it nonpolar or polar? If they're both the same, they'll probably dissolve. Nonpolar and nonpolar, polar and polar. But if they're different, they probably will not dissolve. Those are generalizations.